Welcome back to Applied Mathematics. In this video, I want to talk about volume formulas, volume units, and other concepts related to volume of solid figures. Let me get my head out of the way, and much like when we talked about area, I want to start off by talking about what we mean when we talk about a volume unit. And so to do that, I need to first draw something that resembles a cube. And I'm going to go ahead and call this a cubic yard. Why did I choose yard? Because 1 yard is 3 feet, and that's the smallest division that exists in length units that I know of. So a cubic yard, we could also write as a yard to the third power. Is the volume of a cube which measures 1 yard by 1 yard by 1 yard. Then, since 1 yard is 3 feet, I can divide this up into 3 feet in that direction. I can divide this into 3 feet in that direction. And in that direction. And if you think about trying to count this up, all told, I end up with 27, right? There's 9 in the face, and then there's 9 more in the second row, and then there's 9 more in the back row. 1 foot by 1 foot by 1 foot cubes. So 1 cubic yard is the same thing as 27 cubic feet. The dimensional analysis pans that out. If I want to do the conversion, I'll write 1 cubic yard over 1. I'll multiply that by 3 feet in 1 yard. But because this is yards cubed, that means that there's 3 factors of yards, which means I have to do this not once, not twice, but 3 separate times. So that the 3 factors of yards combine to cancel out the 3 factors in cubic yards. And when we do that, we get 3 feet times feet times feet, which will be feet cubed. We get 3 times 3 times 3, which is 27. So 27 feet to the third power, or 27 cubic feet. Just like square units for area, whenever you're dealing with volume units, whether you write cubic yards with the abbreviation or with the exponent, you have to remember that that exponent means 3 factors of yards and write it out. Same thing if you're converting from cubic feet to cubic inches, or from cubic centimeters to cubic meters, or whatever your particular units happen to be. Right. The naming of three-dimensional objects can be a little bit weird. A rectangular prism is a box. Which happens to have a rectangle as its base. So the rectangle has dimensions length and width, then there is a height, and the volume is the product length times width times height. A triangular prism is probably the most challenging, well, the second most challenging of all the figures I want to talk about today for me to sketch out, but I'll do my best. A triangular prism has a triangle. As its base, and projects out into 3 dimensions. As we've talked about previously in triangles, well, we've called this base and height. I'm going to go ahead and continue doing that. Let's still call this the base, but I'm instead going to call this A for the altitude so that I can use height to describe the distance between the 2 triangles on the front and the back. And the volume here will be 1/2 times that altitude times the base times the height. All right, let me shuffle some things around a little bit. I would like to fit all 3 of these on the screen at once. So let's just tuck these formulas kind of a little bit out of the way so that I can also deal with the right circular cylinder. All right, the right circular cylinder is a can. We've got a circle. I'll draw it at the top and the bottom. You could also draw it on the left and the right. That circle has a particular radius. There is a height of the cylinder, and the volume here is given by the formula pi r squared h. All of these formulas start to look like alphabet soup after a little while. So instead of trying to remember all of these formulas and all of these names of different shapes, there's a really nifty trick. I say it's a trick, it's actually the foundation of everything. All of these formulas have something multiplied by height. And for all of these formulas, that something is the area of the base. The area of a rectangle is length times width. The area of a triangle is 1/2 altitude times base. The area of a circle is pi r squared. Take that area, multiply it by the height, you get the volume. You can use that for the area of anything. If you have a weird irregular shape and then you cut it out cookie cutter style, the volume is going to be the area of your weird irregular shape times the height, the thickness of whatever you were cutting out of with the cookie cutter. Right? We can challenge my artistic abilities even further. Let's go back to a white pen. We can think about a right circular cone. A right circular cone is a traffic cone or an ice cream cone or whatever else you might want to think about it as, depending on which way it's oriented. It's got a circle on the base, which has a radius r, and then the distance from the base to the tip is the height h. And the volume here is 1/3 pi r squared h. And I couldn't fit everything on the screen. Something had to give at some point. But I want you to go back and look at the formula for the right circular cylinder, which was pi r squared h. By taking that tip, or taking the one side and having everything squeezed down to a point, instead of continuing with straight sides, we end up with 1/3 the volume. That trick works. Once again, no matter what your shape is. If you have a square-based pyramid, which is probably the only shape we're looking at here that is harder for me to draw than the triangular prism, but if you have a square-based pyramid, and you can draw a square-based pyramid, the volume here is going to be 1/3 times the side length squared times the height. And okay, when we talked about a rectangular prism, we had a generically rectangle base. But if the length and width of the prism were both s, then length times width would be s squared, and the volume would be s squared times h. And then because it goes to a point instead of going up in straight walls, we have a factor of 1/3. And then the last shape, I don't have any nifty things to say about it. It's the sphere. The volume of a sphere is 4/3 times pi times r cubed. All right. So, yeah, thinking about a sphere, drawing a sphere, very difficult. Everyone here has held a ball at some point in your life. You know what a sphere is. A sphere has a radius from the center to any point on the edge. The volume is 4/3 pi r cubed. For anyone who is going onward to take calculus, the formula for the volume of a sphere at the calculus level, you learn some very interesting things. But if you aren't planning that journey through to calculus, then I don't really have anything else interesting to say about the sphere, unfortunately. So yeah, a whole bunch of different formulas, keeping all of these straight, hopefully not that bad now that you kind of see how they relate to each other. There is a pattern, there is a logic behind all of this. We could come up with all sorts of other shapes. Right? One of the things that I really enjoy doing is taking my right circular cone and just grabbing that point at the tip and moving it way off to the side so you have a slanty cone. Turns out the formula works the same way. Measure the height perpendicular to the opening and you have the same formula, everything still works fine. That's a little bit beyond the scope of what I want to get into in this video, so in order to prevent me from rambling and going on forever, I have to end the video somewhere. How about here?